So we said that there are three ways generally of relocating heat or thermal energy from location A to location B. One of those ways I'm going to talk about now is radiation, and that doesn't need any matter. That doesn't need any atoms or molecules. The other one we said was convection. And convection is where we are a blob of warm air, or I guess it would be warm air. Convection is where a blob of warm air or warm fluid, so it could be a liquid, relocates. And in that sense, it takes its thermal energy with it. And we said, actually, remember that if you have a chunk of warm air, it's going to be lighter, less dense, more buoyant, and it's going to want to rise. And that's convection. And then the last one I'm not going to talk any more about was conduction. And conduction basically is if this is a metal rod, and if I heat the metal rod down here, eventually that thermal energy or that heat is going to get over to the other end, and that is via what we call conduction. Okay, and what's happening is molecule to molecule to molecule to molecule. It's like going down the chain. It's like bumping each other. But I want to talk more about radiation. And actually, heat, thermal energy, is actually only one form of a broad family of energies we collectively call electromagnetic or EM radiation. But all those little different forms of electromagnetic radiation, like infrared radiation, thermal energy, have some things in common. One is that they travel in waves, kind of like if you were to drop a pebble in a pond, you kind of see those waves, those ripples. Okay, kind of think of that's how these energies are traveling. All forms, different types of electromagnetic radiation, have an electrical and a magnetic component, and they are in phase. Okay, they're kind of traveling both together at one time. So here we go. Here are some, you probably recognize some of these names. Okay, I mentioned, and we can add IR or infrared, or this is thermal energy, is a type of electromagnetic radiation, or can be transmitted by electromagnetic radiation. X-rays, visible light, falls into this is a member of the family of energies we call electromagnetic radiation. Radio waves, and there's more I'm going to show you. And we use the word spectrum to kind of show or display all of these different forms of electromagnetic radiation. It's a beautiful thing. So when the sun, and we're not going to talk much about kind of the sun's power per se, but just know that when the sun beams in all direction, its energy, it basically hits all of these different types of radiations: X-rays, visible light, radio waves, of course, infrared radiation, ultraviolet, all of that stuff. And all of these different members of these family, this broad family of different types of radiations, they all travel at the speed of light. And the speed of light. And the speed of light in the English system is about 186,000 miles per second. Metric speaking, it's 300,000 kilometers per second. Right? Pretty darn fast. So I mentioned that we kind of think of electromagnetic radiation energy traveling kind of like waves of a pond, that sort of thing. And so it's important to talk about the repeating, what we call wave. And we use the term lambda. It looks like an upside down V right here. Upside down V with kind of a tail on the top. We use that, and actually it kind of looks more like this. We use that to indicate something called wavelength. And I'm going to show you what the wavelength is. You kind of see the green and the blue here. That would be the electric and the magnetic component of this particular form of radiation traveling. You kind of see in the purple air is kind of showing you the direction. But what I want you to focus on is that here we have this lambda sub A is talking about to complete one wave cycle of that particular energy. And so you have to go through one crest, through one trough, and back again. Okay? And literally it's a distance. It's not going to be, well, some of them are going to be centimeters. Okay? But that's the wavelength, and it's characteristic of each form of electromagnetic radiation. Each member of the family has a different wavelength. And in general, the shorter that wavelength, the more energetic, and I guess you would say dangerous to life, I don't know, the more energetic that particular form of energy. The shorter, the more energetic. So here again, I'm just kind of over here emphasizing pulling out one repeating unit. So that would be the wavelength. So my last thing up here says, notice that the wavelength of energy A is significantly shorter than the wavelength of energy B. And so we would say, this is longer. And so we would say that this is more energetic. And this is, oops, I should put the word there, more there. And this is less energetic. Wavelength. It's important because I'm going to go ahead and show you the spectrum of the different members of the family that we collectively call electromagnetic radiation or EM radiation. Starting with the shortest wavelength. Gamma rays, I don't think I want to be hit by them. Okay, X-rays, and there's some overlap here. Down here along the x-axis, you see wavelength. These are wavelengths. Then a little bit longer than X-rays, we have ultraviolet, and again, notice the overlap. A little bit longer than ultraviolet, we have the energies that are so important to us so we can see things, visible light. And then a little bit longer than visible light, we have infrared. Notice that infrared can be broken up into near infrared and far infrared. A little bit longer than infrared, we have microwaves. Longer than microwaves, we have radio. Radio waves are a form of electromagnetic radiation. All of these travel at the speed of light. So you're going to want to kind of become familiar with these different types of energies from shortest wavelength to longest wavelength. What I was thinking was when you go to take your Unit 1 exam, remember you can bring with you a note card, a 4 inches by 6 inches note card front and back, and you might want to put these on your note card.